My name is Chandramouli, a lecturer in mechanical engineering, worked at Government Polytechnic, Warangal. So, my subject engineering materials. So, in that major topic, iron carbon equilibrium diagram. So, today we will deal with subtopic isothermal reactions, teaching aids, diagrams, and animations. So already previous class we have seen the critical points, that is the critical temperature lines A1, A3, A13, ACM, A2 and A4. These are the critical temperatures or critical points by heating or cooling, whichever may be doing by the binary system alloy, iron carbon alloying by the internicial solid solution alloying. So by study the equilibrium diagram or phase diagram. So temperature is on y-axis, percentage of composition, that is carbon on x-axis. So by cooling we will analyze the iron carbon equilibrium diagram. So with the help of equilibrium diagram, which phases occurs in the presence of carbon and temperature, with type of structure, with type of phases or occurs, we will study the iron carbon equilibrium diagram. Based on that, previous class we have discussed critical temperatures. The next today's class we will discuss isothermal reactions. What is the meaning of isothermal reaction? At constant temperature, what is the reactions in the binary system, that is iron carbon alloy, that is the internicial solid solution alloying. So recap, the last class we have discussed about iron carbon equilibrium diagram, phase of iron and carbon alloy, and critical points A1, A3, A13, ACM. That means hypoelectroid steel for lower critical temperature and higher critical temperature. Like that, hyperelectroid steels lower critical temperature and higher critical temperature, and A2 and A4 is the critical points in the iron carbon equilibrium diagram. So today, objectives of today's program: on completion of this period, you would be able to understand and know the thermal reactions. Thermal means at constant temperature. T is equal to C. Constant temperature, there are three reactions are getting. That reactions are periodic reaction, reductoid reaction, and eutectic reaction. These are very three invariant reactions in the iron carbon equilibrium diagram. This is the iron carbon equilibrium diagram. So already you will see the in iron carbon equilibrium diagram 0 to 2% is called. So temperature is on y-axis, percentage of composition is on x-axis. Temperature is on y-axis, percentage of composition is on x-axis, and 0 to 2% is called steel, and 2 to 6.67 is called cast iron. So the maximum content of carbon alloying or mixing in the iron is 6.67%. So in that classification, 0 to 0.8 is called hypoelectroid steel, and 2 to 6.61 is called 0.8 to 2% is called hyperelectroid steel. Means hypo means some extent, 0 to 0.8. Next, more than 0.8 is called hyper, the more than. That means hypo and hyperelectroid steel, hyperelectroid steel. So like this, 2 to 4.3. 2 to 4.3 is called hypoeutectic cast iron. Hypoeutectic cast iron, and 4.3 to 6.67 is called hypereutectic cast iron. Hypereutectic cast iron. So these all the main classification of composition. And last class we will see the critical temperature lines, that is the PS is the A1 that is lower critical temperature line for hypoelectroid steel, and A3 is the upper critical temperature, that means GS is the upper critical temperature line for hypoelectroid steel. So like that so A13 is the lower critical temperature line for hyperelectroid steels. A13, that means SP, that means SK, SK line is the A13, that is for hyperelectroid steels. Next SC is the ACM. SC is for upper critical temperature. SC is the upper critical temperature line for hyperelectroid steels. These are the critical temperature lines. So like this, A2 is the Curie point temperature line. So below the A2 line is called all our magnetic property, that is ferromagnetic properties. Above A2 is called non-magnetic properties. తెలియదు నాన్న, మిర్రర్ కార్డు చూడుపా. సో A2 is the below the A2 line is called what is this? This is the non-magnetic property. Above is called non-magnetic property. That's why A2 also is the critical temperature line like this. So A4. So you will see the A4 also in line AB is the A4 line. A4, that is the A4 line. Okay. So today's we will see the also last class we will see the critical temperature, that is critical points. Today's we will see the how the isothermal reactions are getting in critical points. How the isothermal reactions are getting in the points. So there are 3 horizontal lines. So this diagram also very easy to construct. So first we will draw a rectangular box. So in that, so baseline we will draw first baseline, and next at 723 degrees centigrade we will put another line, and 1130 degrees centigrade another horizontal line, and finally at 1492 degrees we put another line. So that is the horizontal lines, that is called constant temperature lines, that is the isothermal lines. So you will see the today's isothermal reactions. 3 horizontal lines. First one is the HJB. You will see first one is the HJB. First one is the HJB, second one ECF and PSK. So first one is the PSK. Okay, next second one is the HJB. Where is the HJB? So in the top you will see HJ, HJB. This is called first one. HJB is the three isothermal lines. HJB. Next ECF. Second one is the ECF. Third one is the PSK. These three are the in the diagram indicates the isothermal reactions in the fixed composition and temperature. In these three, you will in this year we will consider the phase transformations at these three places. At the three places are temperature also constants. At 1492 degrees centigrade, that is called HJB, and 1130 degrees centigrade, that is called ECF, that is called ECF, and 723 723 degrees centigrade, that is called PSK. These three horizontal lines, that is HJB, ECF and PSK in the diagram indicates the three isothermal reactions at the fixed composition and temperature. So this is the iron carbon equilibrium diagram, total construct iron carbon equilibrium diagram. So you will draw three rose flowers with three horizontal lines. These three diagrams are easily construct. So you will see the animation how to construct this diagram. So first you will see the eutectic reaction. So first you will see the periodic reaction. So periodic reaction is occurs at the top, means iron has a polymorphism or allotropic form. That is delta iron, gamma iron and alpha iron. So in the delta iron, this periodic reaction takes place at the formation of the austenite at the 0.18% of carbon at the constant temperature 1492 degrees centigrade. From the liquid and solid phase gives rise to another type of solid. So liquid plus solid gives rise to another type of solid is known as the periodic reaction. This periodic reaction takes place at 0.18% of carbon and 1492 degrees centigrade. 1492 degrees centigrade. So that means delta iron plus liquid form of iron gives rise to by using cooling or heating. It is a reversible process. That gives the stable form of iron. Austenite is the FCC structure. So that is the most useful form of iron. So that is liquid means iron liquid form plus delta iron means gives the cooling or heating gives the austenite. So we will see the austenite means HJB. This is H 0.08% HJB. So here delta plus liquid is there. Total this interface. So ABCD is the liquidus line. ABCD is the liquidus line. ECF is below is called solidus line. Okay, we will study this diagram. AHCD is the top, all are liquidus line, that is molten state of the iron. So AHJECF is the solidus line. So this intermediate phase, both liquid plus solid or exist. Okay. both liquid plus solid exist. So you will see the first construct the x-axis, y-axis. So y-axis on temperature, x-axis on percentage of composition. So the composition also very important. You will study only 0, 0.8, 2, 4.3, 6.6, and why you will go for at a particular type of this composition means in that particular type of compositions only the phases or changes and required phases or required structure or stable components are occurs. That's why we will study the only 0, 0.8 to 4.3 and 6.67. So first reaction, so that is called periodic reaction at the point H in diagram is there. Point H 0.08 percentage of carbon and 1419 to 1492 degrees centigrade. Here delta plus liquid iron gives rise to delta plus liquid intermediate phase gives rise to austenite phase. Austenite phase at the temperature 1492 degrees centigrade and 0.08 percentage of carbon. So this it is a chemical name. Periodic is known as a chemical name. That means liquid plus one form of solid gives rise to another type of solid too. This is called periodic reaction. This is called periodic reaction. Okay. This is the very important at the point H 0.08 percentage of carbon. There is temperature and composition, both are very important for construct the equilibrium diagram. Construct the equilibrium or phase diagram. This is the first reaction complete isothermal reaction. It means at constant temperature. That's why these are called isothermal reactions. Okay. Next go for second one. This is the periodic reaction. So second one go for eutectic reaction. So the solidification of liquid at 4.3 percentage of carbon at a constant temperature 1130 degrees centigrade into two phase mixtures, that is liquid form of iron by heating or cooling gives rise to two types of solids, that means solid 1 plus solid 2, that is austenite plus cementite. This total mixture is called laborite. The eutectic mixture of austenite and cementite is called laborite. So you'll see the diagram. At the point C. Above already you told, so A, B, C, D is the liquidous line. So that is molten state of iron. In that point, so liquid gives rise to austenite plus cementite. Austenite plus cementite. That means one type of liquid gives rise to by heating or cooling gives rise to two types of solid, that means solid 1 plus solid 2, solid 1 plus solid 2. So that's why this type of chemical name, that means this type of chemical reaction is called eutectic reaction. So at exact 4.3 percentage of carbon and 1130 degrees centigrade, 100% of laborite is forming. 100% of laborite is forming. This is the very important. That's why you go for 2 to 4.3 is eutectic reaction. Why 4.3 to eutectic means that is the main reaction. That means liquid gives rise to two types of solid. That means solid 1 plus solid 2. Solid 1 plus solid 2. That's why it is a eutectic reaction. So the solidification of liquid 4.3 percentage of carbon at constant temperature 1130 degrees centigrade into two phase mixtures. That is, liquid gives rise to austenite plus cementite. Austenite plus cementite, that is ladderite. Total mixture is called ladderite. Heating or cooling. So the eclectic mixture of austenite and cementite is called ladderite. So next last isothermal reaction is called electrolyte reaction. Electrolyte reaction. So the decomposition of austenite occurs 0.8% of carbon at a constant temperature 723 degrees centigrade into ferrite and cementite is known as a electrolyte reaction. Why you call it octide? That is a chemical form. Why means so one type of solid gives two types of solids. That means austenite decomposes by heating or cooling in the form of ferrite plus cementite. That is called total mixture is called perlite. So the tetratoid mixture of ferrite and cementite. The tetratoid mixture of ferrite and cementite is called perlite. The tetratoid mixture of ferrite and perlite is called perlite. So you'll see the iron carbon diagram at that's why here we will why we study means 0.8 in that percentage of composition only these phase transformations are occurs. That's why you will study that isothermal reactions, the temperatures. So at exact 723 degrees centigrade and 0.8 percentage of carbon. So austenite is gives rise to so solid one gives rise to two types of solids, that is called ferrite plus cementite. Ferrite plus cementite, exact 0.8 percentage of carbon, total 100 percentage of ferrite occurs. So this is the very important reaction. So that is called electrolyte reaction. So phases in iron carbon system. So liquid. So already we'll discuss all this. Okay, once again we will see this type of liquid, that is symbol L means liquid solution of iron and carbon. So delta ferrite means delta iron interstitial solid solution of carbon. So delta iron with high temperatures BCC phase. Austenite. So austenite is the gamma iron interstitial solid solution of carbon in gamma iron FCC phase. So ferrite interstitial solid solution of alpha iron in carbon at room temperature BCC structure. It is the softest material. So cementite, so that is called Fe3C. So intermetallic component of iron and hardened brittle metal orthorhombic system, orthorhombic structure, that is called phase. This is a ferrite structure, microstructure for ferrite. That is a very large size of grains. This is called austenite microstructure. So these are called invariant reactions. The horizontal lines always indicates an invariant reactions in the binary phase diagrams. So periodic reactions to delta iron plus liquid gives rise to austenite. Austenite eutectic reaction, that means liquid gives rise to liquid gives rise to cementite plus austenite. Cementite plus austenite. Eutectoid reaction is gives rise to one type of solid, that is austenite is gives rise to ferrite plus cementite. Ferrite plus cementite. These are all the invariant reaction. These are all the invariant reactions. Suppose you will see how these eutectoid reactions fraction of cement and ferrite are evaluate, you will see this type of flow chart. The iron carbon equilibrium diagram, how isothermal lines are, how to draw the iron carbon equilibrium diagram. You see the animation for this.
The basic sequence of steps you may follow. Firstly, draw the temperature as y-axis and the percentage of carbon, which is the basic iron carbide which we get. So the carbon is being varied from 0 to 6.67 percentage of carbon. So carbon is being alloyed. Now when we do that, mainly iron is accepts the carbon in the interstitial solid solution form. Now I hope you all have remembered about the solid solutions mainly take place in two forms, one in the interstitial solid solution type and other in the substitutional form. Now iron carbide phase diagram, the carbon elements are in the interstitial positions of iron crystal lattice structure. Now when we do that, the carbon, the maximum it can be formed in iron is up to 6.67 percentage of carbon. What exactly happens at this 6.67 percentage of carbon is it forms an interstitial compound. Now mainly you need to understand there are three things. One is pure iron, then alloy, and then compound. If and only if alloy is formed when they obey Huminotherese rules. When they fail to obey the Huminotherese rules, it will end up forming a compound. And we have in iron carbide phase diagram one such compound which is at exactly 6.67 percentage of carbon. So many will have a misconception that what is this iron carbide? Iron carbide is just a percentage of carbon. It's not a phase. And at this 6.67 percentage of carbon, it forms iron carbide, which is represented by Fe3C, or also called as iron carbide, or commonly called as cementite for a common metallurgy aspects. Now, the iron can be varied from 0 to 6.67 percentage of carbon. So, this is the boundary that which is formed for representing iron carbide phase diagram. Now, upon this, we are going to start with the same type of cooling curve temperatures that like we have seen for pure iron, except that when the carbon is being alloyed, you will get a range of temperatures over which the transformations will take place. Unlike in the pure iron, it transforms at a constant temperature. So we have to start with the liquid transformations. So first let us just draw sequentially how the transformations takes place. Now this is the sequence of steps you need to remember in order to draw the iron carbide phase diagram. This is the only step that is to be remembered. Then when we have discussed the pure iron temperatures, more or less the same similar temperatures will also follow in the iron carbide phase diagram. So it's starting with 1539, then we have one intermediate which is 1492, then 1400 again, then another intermediate which is 1147, then 910, and now 723. These are the temperatures which are represented in degrees centigrade. Now, like I said, above 1539 degrees centigrade, we have liquid, which is this line is our liquidious line, above which everything will be in the liquid state. Then below 1539 degrees centigrade, at this location, you'll get delta iron. So like we have already discussed, from 1539 to 1400 degrees centigrade we have delta iron. Now below delta we have gamma from 1400 up to 910, which is in this case austenite. We'll come back to that. Then below 910 we have alpha iron, which is ferrite. We will again discuss that ferrite in shortly. Now it is very easy to mark the other phases, the two phase regions. Like in this side we have liquid, here we have delta, so this will become liquid plus delta. Similarly, here delta, here gamma, so in between you will get delta plus gamma. Likewise, you have gamma plus liquid, and then L plus Fe3, that is liquid plus Fe3C. So it is very easy to point gamma plus alpha here. So on either sides, whatever the phases are present, the two phase regions will have those two combination of phases. Next important thing to do is about the compositions, that is carbon composition. We'll start with the top here, which is having the delta maximum composition is 0.1% of carbon. Then you have here in between, which is 0.18% of carbon, and the maximum here it is 0.5% of carbon. And another one at this particular location, which is 4.3% of carbon, and then here it is 2% of carbon, and here it is 0.8% of carbon, and the maximum alpha it is 0.025% of carbon. At room temperature, alpha is 0.008% of carbon. What we can notice here is delta having maximum percentage of carbon at 0.1% of carbon, gamma at 2% of carbon, and alpha at 0.025% of carbon. When a carbon is dissolved in gamma iron, in short, we call that as austenite. And when carbon is dissolved in alpha iron, we call that as ferrite. We'll also come back to that during the invariant reactions. Now, there are three horizontal lines, one at 1492 degrees centigrade, and another one at 1147 degrees centigrade, this line, and the third one at 723 degrees centigrade at this line. So mainly these are the lines which are horizontal, meaning they are the invariant reactions. So in iron carbide phase diagram, we have three invariant reactions represented by three horizontal lines, where we get the invariant reactions, and this occurs, the first one, the first invariant reaction, we call that as a peritectic reaction. This peritectic reaction occurs at this point here. So at 0.18% of carbon and 1492 degrees centigrade, the liquid plus delta iron will combine to form a new solid, which is called as gamma iron. That is, liquid plus delta iron gives rise to austenite. This is our first invariant reaction occurring in iron carbide phase diagram. The next one will occur somewhere here at 4.3% of carbon and 1147 degrees centigrade. This is we called as a eutectic reaction. So in eutectic reaction, at 4.3% of carbon and 1147 degrees centigrade, liquid will transform into ends of the line. You can see very clearly this end we have gamma iron, which is austenite, and this end it is Fe3C, which is cementite. So liquid will transform into austenite plus cementite, and this mixture is called as ledaburate. That is, austenite plus cementite mixture is called as ledaburate. The next, the last one, the third invariant reaction occurs here at this point, which is at 0.8 percentage of carbon and 723 degrees centigrade, which we call it as a eutectoid reaction. So at 0.8 percentage of carbon and 723 degrees centigrade, we have eutectoid reaction, which is again gamma transforming into ends of the line. This end it is alpha and this end it is Fe3C. So the austenite will transform into ferrite plus cementite, and this mixture, ferrite plus cementite mixture, is called as perlite. So this is what you are supposed to remember. Simply 3 invariant reactions. One at 0.18% of carbon, which is a peritectic reaction at 1492 degrees centigrade, wherein you'll have liquid plus delta iron transforming into austenite. Then next, at 4.3% of carbon, eutectic reaction, where 1147 degrees centigrade, liquid will transform into austenite plus cementite, and that mixture is called as lead aburate. Then the third one, eutectoid reaction at 0.8% of carbon, 723 degrees centigrade, gamma iron austenite will transform into ferrite plus cementite, which mixture is called as a perlite mixture. Now here another important thing you need to remember here is austenite, which is formed in the eutectic mixture, will not be stable below 723 degrees centigrade. They further transform into either of the forms of perlite. So austenite below 723 degrees centigrade is not stable, which will again transform, that is this transmission line. Next, we are going to understand that in iron and carbide diagram, we have basically two important engineering metals, that is steel and cast iron. So mainly here in iron carbide phase diagram, from 0 to 2% of carbon we get steel, and 2 to 6.67% of carbon we call that as a cast iron. To be precise, it is 0.008 to 2 is steel, and cast iron, it is very brittle, so maximum we may use up to 4.6 to 4.8, we will not even go up to 6.7. So this is steel definition in terms of composition of carbon, that is varying from 0.008 to 2% of carbon is called steel, and 2 to 6.67% of carbon is called as cast iron. Furthermore, you have two important reactions, which is in steel you have eutectoid reaction, whereas in cast iron you have eutectic reaction. So less than the 0.8% of carbon is called hypoeutectoid steel, and greater than 0.8% of carbon is called hypereutectoid steel. Similarly, in cast iron, less than eutectic composition, which is 2 to 4.3% of carbon, is called hypoeutectic cast iron, and 4.3 to 6.67% of carbon is called hypereutectic cast iron. Now, steel portion of iron carbide phase diagram. When we separate only the steel portion of the iron carbide diagram, this is somewhat it looks like. And in this, we have only focused on the temperatures from where austenite is transforming, and the carbon ranging from 0 to 2% of carbon. Like we already discussed, this up to 2% of carbon, it is called steel. Now furthermore, we have to understand something about the lines which are represented here, which is the transmission lines, which are also called as critical temperature lines. Now we label them as A3, A1, ACM and A3, 1. They are also called as upper critical temperature lines and lower critical temperature lines, but they are on the either sides of the eutectoid temperature line. So in general, they are called as A3 is called as upper critical temperature line on the hypoeutectoid side of the steel, and A1 is low critical temperature line on the hypoeutectoid side of the steel. ACM, similar to that, upper critical temperature line on the hypereutectoid side of the steel. and A3,1 is lower critical temperature line on the hyper eutectoid side of the steel. Sorry about this. This is hyper eutectoid side of the steel. Now, if at all we take an alloy composition somewhere at 0.4 percentage of carbon, and we try to understand the microstructure or the cooling of this 0.4 percentage of carbon, something like this. So at austenite we have somewhere at this particular point we get altogether austenite composition throughout with 0.4 percentage of carbon dissolved interstitially in the austenite grain boundary, and it will not have any difference until it reaches this line, which is A3 line. So it will have the same 0.4 percentage of carbon in the interstitial portion of the iron lattice up to the upper critical temperature line on the hypoeutectoid side of the steel. Upon reaching this line, just below that, this is where the allotropic change has to start. Like we have already seen in pure iron, the allotropic change has starts from 910. Since carbon is being added, there is a difference in the temperature at which it is supposed to occur. Instead of 910, it is occurring somewhere here below. And at this temperature, the starting or the beginning of transformation is to initiate, and it will transform from FCC gamma iron to BCC alpha iron, and the allotropic change is beginning at this particular point. So all the allotropic changes is initiated just below this upper critical temperature line on the hypoelectric side of the steel. Now, in order to change from FCC gamma iron austenite, the carbon which is present in the interstitial solid solution has to come first out, and they have to just dissolve only 0.025 percentage of carbon and form a alpha iron like shown in this case, and the rest of the carbon which has come out from the gamma iron will be absorbed by the other gamma iron or austenite, and that is how the austenite will increase its carbon content and will try to attain the eutectoid composition, which is 0.8, and it only dissolves 0.025 percentage of carbon in order to form alpha iron. And this alpha iron which is formed will grow in size from this point until it cools to this point. So as it cools down, the amount of ferrite which is formed will only vary, but at the same time the rest of the austenite will attain more carbon, and it will try to attain the 0.8 percentage of carbon, which is exactly required for the eutectoid reaction to participate. So below this line, or the eutectoid temperature line or lower critical temperature line, all the austenite will attain 0.8 percentage of carbon, which is exactly required for the eutectoid reaction to occur, and the austenite will now transform into the eutectoid reaction, which is nothing but ferrite plus cementite mixture, which is perlite. So it looks something like this. We'll come to this perlite formations, but mainly you'll have the austenite which is transforming into alternate layers of ferrite plus cementite, like shown in this case with the hashes, and the alpha which is ferrite which is formed even before the eutectoid reaction is called as pro-eutectoid ferrite. So in 0.4 percentage of carbon we get pro-eutectoid ferrite and perlite mixture. Now when we discuss about 0.8 percentage of carbon, at this particular point it will have more or less the same austenite, only difference will be its carbon content. In this alloy we have 0.8% of carbon dissolved interstitially in the austenite grain boundary, and at this particular point, it behaves like a pure metal and completely transformed. 100% of austenite will be transformed into 100% of pearlite. So it will all transform into alternate layers of ferrite and cementite network, like a laminar or a fingerprint like structure, as you can see here in this case. So main process behind this transformation of austenite to pearlite is through diffusion. So the carbon which is coming out from the austenite will form first initially a plate-like structure, which is a rich in carbon. So it will form a the same austenite, but in this case below this upper critical temperature line on the hyperdetectoid side of the steam, right, at the room temperatures, when we have a carbon composition less than 0.8, which is a high.
So after see this animation, so we will finally today's review. So this is for microstructures for tetratoid steel, hypotetratoid steel, hypertetratoid steels, and this is the final review. Thank you.